All right. Great. All right. I will share my slides. Can everyone see that?
Yep.
Great. Well, thank you very much.
I'm so sorry to interrupt. If you have questions during the presentation, please type them into chat and we'll get them to them at the end. Okay. Sorry.
Okay. Yep. No, thank you very much, Kathy, for that introduction, and for inviting me to this series. This really sounds like a fantastic series, and it sounds like you've got some amazing speakers lined up after me. And so I'm hoping both to kind of introduce the overall set of ideas and to introduce a particular perspective that I have on that. That partially and largely comes out of my work in computer science, where we, for those of you who are not computer scientists, we think about more than just how computers work. We think about how computation is done and how information processing is done. And to a large extent, the scientific enterprise is an information processing system, and how it works can be partially analyzed by certainly things like sociology and psychology, but also how it works as an information processing system. And I'll talk a bit about that. I am happy if there's a particularly confusing point on a specific slide. I'm happy to take a question then, but I think I'm definitely going to leave some time at the end for questions and discussion, because I think there's a lot to discuss about this topic. So let me start out first and just try to give a reasonable definition of what the reproducibility crisis is. For those of you who may not be familiar with the term, I think most of us have probably gotten a sense of that. But unsurprisingly, Wikipedia has a very good definition: an ongoing methodological crisis in which it has been found that many scientific studies are difficult or impossible to replicate or reproduce. The replication crisis most severely affects the social sciences and medicine, but there is data indicating that all the natural sciences are implicated as well, as it says. And I like this definition not only because it refers to it as an ongoing methodological crisis, and correctly says that the real issue is about finding that many existing studies are difficult or impossible to replicate, but also doesn't sort of go into causes necessarily, because I think those are actually fairly murky, and there's some things we're going to talk about today along those lines. By the way, it's also called the replication crisis, or the replicability crisis, or even in some cases the decline effect. That is, that a result is found with a particular effect size and then later found to be much smaller. So unsurprisingly, reproducibility is a persistent concern within essentially every area of science. We are all familiar with the idea that we want to produce science that could be replicated by others, and that others are going to find the same thing if they go looking in the same way. And we're also, many of us, familiar with examples where science did not replicate, and in fact, that resulted in an advance, or at least not in a mistaken perception. So this is a diagram that showed up in a paper about N-rays. That's like N, like the letter N, in the same way that we have X-rays, okay? And in 1903, there was a report in a reputable physics journal about N-rays, about the discovery of a new kind of radiation. But ultimately, this was found to be a complete illusion, okay? Something that actually wasn't occurring, because they were very difficult to detect, and only a few observers could detect them in darkened rooms under certain conditions. And it was found that even if you substituted a source that couldn't possibly be producing N-rays, you still had the same observations. And this turned out to be more about what happens to the human eye in darkened rooms than what happens in terms of the actual emissions of particular substances. Quite recently, intriguingly, DARPA has gotten into the replication business and has a whole program on how to replicate and how to bring computational tools to replication of social science results. And I think most of us are familiar with the Journal of Irreproducible Results as a humorous take on science. And it's funny because, of course, we want our science to be replicatable and replicable. But I will also point out that replication now, with respect to the replication crisis, is also a very highly public issue for science. We're seeing articles in venues that aren't read by scientists primarily, but instead read by the general public, asking very difficult questions. Is science in trouble? Is there some sort of problem with how science is done, the fundamental flaws at the core of science? Also, this has been an ongoing thing for at least more than a decade. And many people, I think, are looking at it, particularly at a time when we have real concern about scientific literacy and about scientific results being taken seriously, vaccines, public health measures, global climate change, et cetera. Is this somehow eroding public confidence in science? And even my own field of artificial intelligence, okay, is having its replication crisis moment because of some fairly recent results in the last several years showing that some earlier results that we thought were really great really evaporate with very small tweaks to the conditions under which those studies are done. And so all areas of science have been hit by this in different ways, but the fact that it's being publicized more broadly, I think, is one of the reasons that I think researchers are concerned about the replication crisis. So there's a very simple question we can ask that is informative, which is, are there, in fact, a substantial proportion of published studies that fail to replicate? Or is this kind of an anecdotal thing? And really, it's not anecdotal. There have been several good pieces of work that have attempted to systematically replicate major findings in different fields or have reviewed older studies to find out how well more recent studies replicated those and have found real problems. So there's good evidence that the answer to this question about failure to replicate is yes. So for example, a study by John Ioannidis, who's familiar to some of you in medicine, and I actually teach some of his, recommend some of his articles to my students in computer science. In one set of results that he looked at, out of 49 medical studies that were published from 1990 to 2003, that were highly cited, 45 of them, the vast majority, claimed that the studied therapy was effective. And out of those studies, 16% were contradicted by subsequent studies. 16% had, it was discovered that the effect was really much smaller than they had found in the original study. 44% of them were in fact replicated and 24% were essentially unchallenged. So if you add together those last two numbers, okay, 68% of the studies turned out to be supported by subsequent literature, but the others did not. And that's a larger number than we would like. A very similar number was produced by a study of major social science studies that were published in Science and Nature between 2010 and 2015. Only 67% of those studies replicated. And in a similar study of major publications in economics, only about 61% of the studies that were published in two of the major econ journals, and these were experimental economics, so doing experiments with human subjects, only 61% of those replicated. Now, I say sort of easily, oh, they were not replicated, and we ought to talk more about what that actually means. The Ioannidis quote is very nice because he says, look, some of them were just flatly contradicted and some of them were found to have weaker effects by the subsequent studies. So let's look a little bit more carefully at that. So this is one of those, this is the second one that I had in my previous slide. This is a graphic from the Kammerer et al. Paper in 2018, looking at a set of social science studies that appeared in Science and Nature. And what we have here is a graph where 0 is no effect, okay, on the x-axis. One is the effect that was actually observed in the original study. So if one of these diamonds, the blue diamonds, appears at the 1.0 mark, that indicates a replication of almost exactly the same effect. And then, of course, we have a 95% confidence interval on that replication. And what's disturbing here is that, first of all, only one, or maybe you could say two of the studies had a larger effect on replication than they did in the original study. The vast majority have a smaller effect, and many of those effects include zero within the 95% confidence interval. That's disturbing. It should be disturbing, because what we would like, of course, is to have something where at least it's evenly distributed around one, and certainly not including zero in that confidence interval. Very similar graphic shows up for the study on the economics studies that showed up in the American Economic Review or the Quarterly Journal of Economics. Again, here 1.0 is that standardized effect that was observed in the original study. And again, here we see that most of the effects are smaller, and many of them include zero within the 95% confidence interval. Now, I've got to say that the Clip et al. Should be very happy, okay, because the replication showed a stronger effect, substantially stronger effect than was in the original study. And I'll also point out that many of these authors, when this work was sort of brought to their attention, in some cases, some of the authors said, no, you're wrong for the following reasons, and disputed the results. A few of them, though, said, clearly, you're right, and in a few cases, they've even tried to reproduce it themselves, and had, in general, similar results to what's shown here. Going back to medicine, there's a very interesting piece of evidence that John Ioannidis has in one of his articles in 2008, where he looks at a large number of meta-analyses that have been done under the Cochrane review system. And for those of you who are not familiar with Cochrane reviews, they are systematic reviews done of a large literature, large number of studies in a particular question, in an effort to provide a kind of consensus answer from the literature. They involve a great deal of work by a large number of people, not only the people who did the original studies, but also the people who do the review, in order to try to come up with reasonably definitive answers about whether certain kinds of particularly medical treatments work. This is a graph of a large number of the Cochrane review meta-analyses, showing not definitive evidence that there's a problem, but evidence that is certainly consistent with the idea that there's a problem. Because here, the larger the sample size, the smaller the odds ratio here, which is a measure of the effect of the treatment, say, given compared to some control. And what we see is that very large effects that show up in Cochrane reviews tend to be associated with very small sample sizes. And smaller effects consistently are associated with large sample sizes. And what we would like to see is that there shouldn't really be any relationship between the observed size of effect and the sample size, if these reviews were kind of all resulting from a kind of unbiased sample of studies. Unfortunately, there seems to be some kind of consistent bias here that smaller studies show larger effects, and then when you put those together into a meta-analysis, you also have a larger effect than you would observe if you had a larger sample size. So there is some evidence, some reasonably strong evidence, I think, that in a variety of scientific fields, published results, major published results, are failing to replicate. And I will point out that this kind of, two-thirds of the studies replicate that seems to come out of the things that I've cited are all in cases where those studies were published in highly, highly respected journals. So these are the top journals in their respective fields. You would expect that the numbers would even get worse when you went down to sort of lower quality or lower review intensity venues. And so, and also when you're looking at things that have only appeared in bioRxiv, say, or arXiv for computer scientists and physicists. So in preprint reviews, you would definitely expect to get a lot lower replication rate. So there does seem to be some evidence, but the replication crisis implies that something is happening fairly recently. And so I think a more interesting question to ask is, has the proportion of studies that fail to replicate increased or decreased in the past decade or 2 decades or 3 decades? That would be a very interesting question to be able to answer definitively. And unfortunately, to my knowledge, we really don't have any good evidence on that question. We don't know that it's going up or down. What we know is that when we've done these reviews, which have really only been done quite recently, we found what seems to be a larger number of non-replicating studies than we certainly want, or than some people at least expected. Also, if we were even able to do that kind of quantitative analysis, my sense is that the interpretation of the answer would depend a lot on whether we believe that the research questions that are being studied are easier or harder than they were 10 or 20 or 30 years ago, and whether maybe we have better technologies or maybe something has happened that made things worse. It'd be very difficult to interpret. So we don't have a good answer to this. There is one intriguing piece of evidence that I'll get to in a minute, but I just want to point out that by calling this a crisis, people are implying that they know the answer to this question, that things are really bad and worse than they used to be. And my sense is we certainly don't know the answer to that, and I don't have any good evidence that things have gotten worse. My tendency is to think that they probably haven't. So somehow we're calling this a crisis, and I will talk about why that is, I think, a little bit later. One really intriguing piece of evidence we do have comes from a recent paper that I'll mention a little bit later in more detail, where they looked at a set of social science studies, 44 reviews. These are reviews of papers published in journals, looking at the average power, statistical power of those studies. And what you'd hope is that if things are getting better, all right, we should be seeing higher power results, that is larger sample sizes and kind of better statistical methodology and better sample sizes. And they conclude that we're not, okay? We're not getting better from the period of about 1960 to about 2015. So interesting result of power isn't going up, so things aren't getting better, but again, no evidence that things are getting worse. So of course, being a researcher in causal inference, I'm particularly interested in what the causes of the reproducibility crisis are. And in particular, I think here what we ought to ask about is what's causing the perception that there is a reproducibility crisis. Again, I'm not arguing that it's good that we're not getting, roughly a third of our results replicating. But there's this idea that there's a crisis, I think is partially a matter of perception. So specifically, what I want to ask about is what is causing the perceived increase in the number and frequency of cases in which published results fail to replicate. And specifically, I want to contrast 2 potential explanations. One is that something has changed about the quality of individually published results. So if you look at an individual study, the question is, could the quality have gone down over the last several decades, let's say? Or an alternative explanation is that something has changed about the context in which those studies are published and reported. Now, obviously, both of these could be true. They could be true in different proportions, but and there are probably many other possible explanations for the perception of the reproducibility crisis. But I'm going to focus on these 2 because they come up frequently in writing about the reproducibility crisis, and I think thinking of them as kind of poles on an explanation spectrum is a useful one. So there are certainly some trends that are happening in all areas of science that have raised concerns about quality. So there is a greater awareness, I think, recently about what might be called questionable research habits. So there's been discussion of what's sometimes called harking, hypothesizing after the results are known. I saw this first in graduate school, where I read a paper about what's called the Texas sharpshooter problem, which is that you shoot at the side of a barn, okay, and then you go draw the target around the bullet holes, and say, look, I got a bullseye. And the explanation, the connection, the science, of course, is that if you generate enough results, you can publicize only the ones that seem interesting. And I will get to that in a minute. A similar sort of idea is the widely discussed idea of p-hacking, of constantly trying to change your study design in order to get statistically significant results. And this has also been referred to by Gelman and Loken as the garden of forking paths, calling to mind a Borges novel about this idea that there are so many paths that you can go down. Simons et al. Has called this researcher degrees of freedom, okay, that there's a lot of choices we typically have in any study where we can tweak different knobs, and we can continue to tweak them in some cases until we get some results we like, and then those are the ones we publish. And that's clearly not a good research practice, but also at some level, some degree of that is seen as sort of creative, thoughtful work, okay, and coming up with kind of more interesting results, making lemons out of lemonade. But the question is how much readers of the subsequent papers actually understand that that's going on. There have also been a number of very, very highly publicized instances of fraud in a variety of scientific fields, outright clear fraud, all right, where people are completely making up data and results. And this has certainly happened. I think it's happened for as long as science has been undertaken. But I think now we have lots of ways of publicizing that, and they should be publicized in order and punished quite severely. But that is nonetheless something that we're seeing, and I think that people are associating and worrying about being one of the reasons we're having low quality. Another thing which I certainly worry about is a greater awareness of career pressures on young researchers. Peter Higgs, after which the Higgs boson is named, said several years ago, he said, I couldn't be hired now as a physicist. He said, I just wouldn't have produced enough papers, and so I wouldn't get hired or wouldn't be able to do the work that I ended up being able to do. There's an enormous focus recently on paper counts and on citation counts and on things like H-index to just kind of sift through large numbers of applications, and leading to the perception, certainly among my students, that if they don't have huge numbers of papers, they're not going to get a job. And so that kind of pressure has been a concern about a way that it may drive down quality. And finally, I think there's been a greater focus on media profiles, both for institutions, university publicity offices, very sensibly wanting to publicize the great work of their faculty, but also individual researchers feeling a great deal of pressure to put out their research on Twitter and put out their research on social media and make sure that they're constantly cranking out things and being involved in publicizing that work. Gieman and Gieman, Don and Stuart Gieman, both remarkable statisticians, recently put out in 2016 a really good, highly readable article called "Science in the Age of Selfies," and they talk about the concern that more attention is being given to publicity than being given to the actual underlying science, particularly publicizing very early results. And I recommend that. And by the way, I'll put a version of these slides, make the version of these slides available with references to all of these, the full citations. However, so all of those are pressures, but I think there are some fairly reasonable responses that can be made to say maybe we shouldn't be so worried, given the replication rates that we're seeing. Those may be quite ordinary, and that some degree of non-replication is expected if science is working the way that it should, because there's a balance between the costs of not publishing research reasonably rapidly and only and then or holding up research for long periods of time until it's replicated and only then putting it out. There's a balance there to be struck, and the question is, where is that balance? So first, I will just say quite baldly that we shouldn't expect most research to be of extremely high quality. I frequently quote Sturgeon's law to people. Theodore Sturgeon was a science fiction writer, and he was asked about the sorry state of science fiction at some point, and he quite clearly said, well, 90% of science fiction is crap, but 90% of everything is crap. And the philosopher Daniel Dennett, expanding on this, in his Tools for Thinking, an article about 7 tools for thinking, said, look, realize this is true. He said and it doesn't matter whether you're talking about physics, chemistry, evolutionary psychology, sociology, medicine, you name it, rock music, even country western, there's just going to be a spectrum of quality. And I think while we need to try to improve that and move the median, we also need to realize that the system has to account for the fact that there's going to be some not very good research in any system. So at some level, failure to replicate is an inevitable part of research, and we're never going to remove those failures entirely. And if we tried to build a system that did, it would probably slow down science to the point that we would be very unhappy with it. Also, I want to point out a very, very provocative finding in the Kammerer et al. Papers, which is that it appears from evidence in those papers that researchers within a field can often predict with great accuracy the extent to which results will replicate or not replicate. So in other words, researchers in the field, while there may be stuff published, they'll look at it and say, nah, that is actually not going to replicate. And the results that I'm referring to here are shown in the 2018 paper, where they ran a prediction market, a group consensus judgment on a set of experts in a field before they knew the results of the replication work that was done in this paper. They were asked to assess the probability that a particular result would replicate. And these results are stunning, The gold-colored dots and diamonds indicate results that were not replicated, and the blue diamonds and dots indicate results that were replicated. And so you could actually take this threshold at maybe about 0.57 and almost do a perfect job of distinguishing between the results that would and would not replicate here under the criteria that they use in the paper. This indicates to me, and it certainly accords with my own sense, is that in general, expert researchers in a field don't just say, oh, it's published, it has to be true. Instead, they look at the study itself, they look at how consistent it is with existing theory, and they moderate their responses accordingly. And so I think we should be a little bit less concerned about lack of replication than perhaps the press accounts would cause us to be. So now I want to get to the real core of what I'm talking about today, and it's not going to last a long time, but I do want to bring up this idea that how we can think about, from a kind of systemic sense, what's going on within the scientific system. So even if we do everything right, some results aren't going to replicate, so we have to structure our scientific system in a way such that high quality research is recognized. And unfortunately, there are a variety of forces that work against that process. And so what I want to call out is that if we have the structure that frankly we do have right now in science, it is almost guaranteed to produce the kind of bias we're observing in the effect size. I'll just call that out as one example. So specifically, any system that produces a large number of items, such as a large number of potential research findings, and then attaches a number, what I'm calling scoring each of those items with some degree of variance, some variability. In other words, if you did the study again, you'd get a different answer. This results from small sample size, among other things, or just really having a finite sample. So in other words, if you estimate the effect size with some variability. And then you select the item that has the maximum score. That is, for instance, you only publish the most significant findings or the largest effect sizes. That is virtually guaranteed to produce bias in the things that are selected, okay? In other words, the published findings will have inflated estimates of effect size. And this is an analysis that Paul Cohen, a colleague of mine, and I did and show, and this is unsurprising to many statisticians, referred to often as multiple comparison effects. But let me just give you an example of this. So let's say that we have two different studies, okay? And the results of those studies, the effect sizes of those studies, have an actual effect size, here shown with a dotted line. But the study, of course, is not going to get that exactly right. It's going to sample from a distribution that, if all things are running well, is going to be centered around that actual effect size. And so what we'll do is we'll sample from those two distributions. The first study will sample from the first distribution. The second study will sample from the second distribution. And if the effect sizes, the actual effect sizes are what I show here, and the distributions are what I show, we would expect that in general, the second study is going to be the one that's going to have a larger effect size. However, let's ask what happens if all of the studies have an actual effect size, say, of 0. And in fact, we don't have 2 studies, but we maybe have 4 studies. And now we sample from each of these and we pick the one that's highest. What's going to happen? Well, almost certainly that is going to be going to be larger than that dotted line indicating the actual effect size. Right, and so the publishing potential, unsurprisingly, is about large effect sizes, or non-zero effect sizes at least. And so that's the study that's going to be published. That's the study, even though there's been 4 other studies done. And this is sometimes called the file drawer effect, because the other researchers, if they end up with a small effect size or a 0 effect size, they'll say, well, we're not going to publish that, and they'll move on. Now, I want to ask you what happens not when there are 4 studies, but when there are, say, 100 studies or 1,000 studies of something. What's going to happen then? Well, we're going to have a very inflated number, which turns out to be the maximum of the samples from all of those distributions. Now, unsurprisingly, the cartoon strip XKCD has already, talked about this idea. So they want to, the scientists in the cartoon strip want to figure out if jelly beans cause acne, okay, and ask the scientists to investigate. And the scientists say, nope, we found no link between jelly beans and acne. And by the way, probability 0.05. And then they say, well, actually, maybe a certain color of jelly bean will cause acne. So they try purple and brown and pink and blue and teal and salmon and red, et cetera, and it goes on. And wow, one of those studies finds out that green jelly beans cause acne, probability less than 0.05. Now, of course, this comes as no surprise because they've looked at, say, on the order of about 20 different colors of jelly beans, and you would expect one of them by chance alone would be significant at the 5% level. And of course, that's the one that gets published, and that's the one that gets publicized, all right? This multiple comparison effect is constantly in play when we're looking at the way that the system of science works. Now I'll return to this, this idea that I talked about before. Let's say there are 100 studies like this. I've actually shown you the good case, okay, where these distributions are relatively narrow. What happens if some investigator comes along and does a really sloppy job, okay, small sample size, maybe a lot of different options about how the study might work. They're not particularly recording things very accurately. That's going to increase the variability of their results. And guess which study is the most likely to have the largest effect? The one with the largest variance. So we could really get into trouble here. And this is all if they have 0 effect. Now, if one of the studies actually is doing something right and should be showing a positive effect, that study could even be swamped out by the study with large variance. If you're interested in this or you don't quite buy this analysis, I recommend you take a look at the paper. We go into some detail about this with some both examples and some simulations. Now, this idea crops up in a variety of places in science. It certainly crops up in individual studies, okay? We don't even have to think about the publication system. We can just say individual researchers try many different design choices, and guess what? They tend to prefer the ones that lead to substantial, large effects. They say, oh, these must have been the right choices to make. So this can show up within an individual study that has has a garden of forking paths or many research degrees of freedom. Certainly shows up in publishing. That's the one that I highlighted. Many submitted papers, each with different effect sizes, and the large effects tend to get favored. It also shows up in publicity. If you're sitting in a publicity office, what are you going to, are you going to publicize? The one with a big effect or the study with a really small effect that doesn't seem very interesting or important? Well, you're probably going to favor those large effects. By the way, this also affects which studies get replicated. Okay, if you're thinking about replicating a study, what are you going to do? You're going to focus on the one with small effect size or big effect size. Probably you're going to pick the one with big effect size. And then you're going to try to replicate that study. And that's even going to affect which replications get published and publicized. We're going to specifically publicize those with the smallest effect. That is the biggest difference between the original study and the new study. So this idea, it doesn't have to be, the multiple comparison effect can happen, by the way, if you choose the minimum, not the maximum. So the same thing can happen here with replications. So all of these are places in the scientific system where we can get this bias cropping up. Now, there are some trends in science right now that make this even more challenging. So what determines how big the bias is for the multiple comparison effect? Well, number one, the degree of variability, that's number one. Number two is the number of things that you compare, okay? And the third is what percentile of the distribution do you pick? Do you pick the maximum or do you pick the average? If you pick the average, there will be no bias, but if you pick the 75th percentile, it'll produce a different kind of bias. So the number of things you're comparing matters. And we are getting more researchers, okay, every year, vast increases in the number of researchers out there, more papers that they're producing, and more access to papers that have been vetted less frequently or less intensively. So all of these things are likely to make the multiple comparison effect even worse. There's been an amazing case study of this that we've had over the past, say, 18 months. Which is COVID-19 scholarship. Huge numbers of researchers pivoted to try to study COVID-19 regardless of their field of study for reasons we can all understand, okay? And there's a great article in The Atlantic called How Science Beat the Virus and What It Lost in the Process by Ed Young. And by the way, it was one of the articles for which he won the 2021 Pulitzer Prize for explanatory reporting. And I think it's a fabulous article and I recommended it to my graduate students and I recommend it to you. In the article, Young says, while the most qualified experts became quickly immersed in pandemic response, others were stuck at home looking for ways to contribute. And so they used the systems that we have all been thrilled to that as they've come online, systems that make science faster. So you could download data from free databases and run analyses with tools that are online and publish those papers on preprint servers and publicize it on Twitter. And this all became known as kind of swerving outside of your scholarly lane and unfortunately doing some serious damage in the process. And he says the tsunami of rushed but dubious work made life harder for the actual experts who struggled to sift the signal from the noise. And they felt overwhelmed by requests to review new papers because everybody, it seemed, and their brother was putting out a new paper on coronavirus response. So highly recommend that paper. I also recommend another kind of systems analysis of this question of publishing based on a kind of evolutionary analogy called the natural selection of bad science, which talks more about this problem. So I'll end with a couple of ideas about if multiple comparison procedures are at least one important cause of the perceived replication crisis, what can we do about it? How can we use this idea to maybe figure out how we can do better? Well, through the lens of multiple comparison procedures, there are at least 4 things that we could do. The first is to try to reduce the number of things, papers, researchers, okay, that are producing or reporting scientific results. And this seems like a really bad idea, so I'm not going to talk about it, okay? I'm not going to say we need fewer researchers or fewer papers. We can try to reduce the variability of individual items, and this seems quite possible, and I'll talk about it in a minute. We could also not select the items with the maximum score. That is, we could not select the papers with the biggest effect sizes. We could like systematically not publish those. That seems like a bad idea, and that's unlikely to succeed in any event, and so I'm not going to talk about that either. And finally, we can do something which is to retest on new data. That is, after the selection process has been done, we go and we sample again from that distribution, and that is basically replication, okay? Run the study again and see if you can see if the new estimate matches up to the old estimate. That's a fantastic strategy, and that's what replication is all about. So talking about that second item, can we improve kind of individual behavior and reduce variability? I think there are a variety of ways of doing that. We can certainly engage in education and encourage people to have better methodology and not engage in not exploit all the researcher degrees of freedom. We can argue for and promote better research practices like pre-registration, like calling your study design ahead of time and registering it someplace. You can do better at reviewing, higher standards for evidence, or more careful attention to the exact methodology. We can hire based not on the number of papers that people have produced, but rather on the best few papers. We've done this in computer science several times recently, where we said, we're only going to look at the top 2 or 3 papers that a computer scientist has produced, identified by them, okay, rather than taking into account, saying, let's just look at the number and say, wow, they've published so many papers, that's awesome. And publicity should focus more on papers that have been reviewed and confirmed rather than those that have just been released. However, still, even if good people are trying to do all of these things, there's still going to be teams that are going to have strong incentives not to do them, to try to get out more papers faster, and unfortunately with higher variance. So what can we do? Well, the problem with this is that there are lots of systems that reward vast numbers of papers being produced rapidly. Journals are constantly looking for the next big thing. Funding agencies are interested in hot areas. The press wants to report only the latest findings. And even in academia, we get kind of excited about some hot new research area. So we can do better in another way by restructuring the system to change incentives for individuals so that individuals will have the incentive to try to do a better job. We can enable ongoing, rapid, and transparent revision of the scientific literature. This is beyond just errata, where we say, oops, sorry, that result was wrong, but instead have long-term ongoing reviews. One of my colleagues, Andrew McCallum, has proposed having review systems that continue long after the paper is published, where people can go back and say, actually, this hasn't panned out in the long run. Making it easy to tie back to prior work that was refuted or confirmed, for example. We can obviously encourage replicability, allowing high-profile publication only if the research is very easy to replicate. We can reward long-standing replicated results with things like the Cochrane reviews and test of time awards. And we can try to clearly separate revision, whoops, we were wrong about that, from fraud and misconduct, which often now get kind of combined or conflated in ways that they shouldn't. So those are my sort of quick ideas given this analysis, and I have a feeling that the future talks will give a lot of really good ideas about what to do about the replication crisis. And that is my email address, but I'm happy to take questions now. Thank you very much.
Thank you. Clap. Thanks. It's hard not to hear the applause when you're on Zoom, but we have a one question that came through from Elliot Moss, and then a response from Allie, who has many names. So I wonder, Elliot, do you want to explain what you're asking?
Yes, yes. Thank you, Catherine. So, David, I happen to be a participant in a now concluded study, the Cosmos trial of whether cocoa and multivitamin supplements improve health. So they've got a sample size of maybe 10,000 people, longitudinal over 4 or 5 years. But the questionnaires we get ask about gazillion health conditions. So I think about, okay, they're going to find some positive correlation with some health condition or other. So in a study set up like that, how can they adjust for that? What are they going to do to be responsible?
So Ali has identified one of the classical ways of doing it, which is referred to as a Bonferroni correction, which is a kind of correction that you can do if you assume that all of the tests are independent. Now, since then, there have been, since Bonferroni corrections were developed, there have been a variety of other approaches to controlling what is often called the false detection rate, okay, because you can understand the correlation structure among your tests and come up with a way of reducing the bounding of identifying what the false detection rate will be. So that's sort of one way you can do it if you want to just do a one shot, take all your evidence. So
in this case, they could refer back to like, what is the correlation between, I don't know, diabetes and heart disease or whatever.
So yeah, that's true. Yep. And then what you can also just do it in your data. You can actually look in your data and see what the correlation structure is. But also, what you're doing is essentially you're raising the standard to account for the fact that you have looked at all of these different options. At the very least, what you ought to do in the publication is you ought to say, we looked at 15 different possible causes, and here is the ranking of effect sizes. Okay, and I like many people increasingly think that doing some kind of statistical hypothesis test is much less interesting and less useful than calculating effect size and having some bound over that effect size, particularly given the number of tests, the number of different possible effect sizes that you're looking at. Yeah.
We have a question from Ben, and then Anna, who I see has her hand raised. Ben, do you want to talk about this?
Sure. Thank you very much for the talk. I was interested in other strategies to address reproducibility, like sharing data sets, sharing tools, sharing code use for statistical analyses. So thinking about expectations from the NIH when you're submitting grants for sharing your data in the end, or archiving data, as well as when you're publishing in a journal, sharing statistical code so that others can reproduce. And it seems like there's always these stories that keep coming out. Someone else got a hold of someone's code, and then there's retractions or additional edits made. So I was curious what your thoughts are and suggestions for best practices.
So those are absolutely practices that are going to help the problem. And what they're going to do is two things. They're going to make replication easier, all right? So that more people will look at that and say, okay, that's a study I can replicate. And second of all, by requiring those to be available, you are providing incentives for the individual researcher to be careful, because they know that their research is going to be potentially examined more carefully. And so I think that both of those are at play, and that's going to reduce the variability. What we're experiencing in my field is a kind of diversity among researchers and their willingness to do that, to make their code available. I, like many in my field, are becoming sort of less and less willing to look at results that don't have available code, and data, because I look at it and I say, yeah, I'm less confident in that. And I think that's it's reasonable. It's correct.
Okay, Anna?
Thank you so much for this beautiful talk about very important issue. I just had some comments and would like to hear some of your thoughts on that. One thing, we don't want to definitely to restrict researchers in a way, the methodology that is used, they're constantly changing protocols, but I think all of that contributes to problems with reproducibility. And I think one of the ways to deal with that is the consortium, when they have certain SOPs, once they were worked out, that could be used by different groups or the similar systems, the way how you handle similar systems. So certain things could be done by SOPs and then compare with different methods within the consortium. And I think that greatly will decrease the lack of reproducibility. And I wanted to hear your thoughts about revision process, because finding a good reviewer for the paper becomes harder and harder because nobody wants to do this job. I mean, I was trying to find a reviewer for several papers. And when I get reviewers back, it's not a big journal, but the quality of research and the quality of revision is very, very low because people are trying to make big claims. It's not a high profile journals, it's a small journals, but they populate a lot of PubMed places. So I was wondering if actually a reviewer should be a professional reviewer. It's not, because it's unpaid job, right? It's usually the PI gets the paper to review, we know how it works, gives to a student and hardly look at what the student wrote about this, and it goes back to the journal and student is happy to review and just say it's all great, and or asking some unreasonable comments, do a couple of knockout mice if you want to publish here, and so I think this should be done more professionally by maybe paid people, because we know that if you're a journalist writing for the paper, you're getting paid for that, and as a researcher you get funded, you try to publish this and you pay for your paper, but people who are reviewing that, this is a volunteer job from other scientists. So, and most of great scientists don't have time to review articles. So I don't know, what are your thoughts on that, because that's a very important component of our system now. Since you start talking about changing the system, I thought it would be.
Yep.
And thank you.
This is a great point, and I certainly experienced this myself. I'm an action editor for the major journal in our field, and it is incredibly painful to try to find reviewers. Apparently, it's been worse, during COVID, which is sort of I guess a surprise that people are just overloaded. But it is unexpected at one level, because we always thought that the number of reviewers would go up with the number of papers. That kind of made sense. The more people that are submitting papers, the more bigger the reviewing pool is. But I think you're right that what has happened is that lots of people are not being willing to review as many papers as they are submitting. If you think that every paper needs 3 reviews, every paper you submit, you should be willing to review 3 papers. And so let's say, so just as a baseline, that's kind of a requirement. I am very worried about the idea of paying reviewers. But I completely agree there has to be some kind of incentive. I just am worried about what cash sort of indicates. And so I'm not saying this is a solution. One of the very small things we've done in computer science recently is started to recognize really good reviewers with awards, okay? And saying nothing about what papers they reviewed, just saying they did an incredible job of reviewing. And that has been a way to recognize, particularly for junior faculty, the effort they put into reviewing, that we can point to that as on a tenure committee or something and say, oh, they're not just doing reviews, they're doing good reviews. And so that's one small example of a kind of incentive you can provide. But unfortunately, past that, I don't have good ideas about how to provide incentives. So yeah, except just to agree with you about the problem.
Okay, we're quickly running out of time, but Sam has written some comments in the chat, and I wonder if David might like to respond to those.
Yes. So I agree that there is a problem with experts in the field knowing something and non-experts, even including new people in the field, not knowing things, or users of that field not knowing things, and certainly the public not knowing that you should ignore certain kinds of results. This is where I think the option for something like, the Cochrane reviews come in, although those typically happen much later in the process. But some way of trying to provide kind of expert opinion, and this is one of the reasons I think this idea of having review systems where I can contribute reviews for a paper even though it was published 5 years ago, that would give a kind of ongoing sense of how the community thinks about key papers in the field, and would give outside people some kind of ability to look at that and get a sense of what the existing feelings or consensus is on a paper. Yeah.
Well, great. Thank you so much, Dr. Jensen. Do you have any closing
Absolutely.
thoughts before we wrap it up?
Nope, those great questions. Thank you so much for all the questions. These have been really interesting, and I'm happy to talk about this. I could probably talk longer than most people could listen, so I'm happy to talk if you have other questions.
Awesome. Well, thank you so much once again, and thank you everybody for attending. We could find a way to show our appreciation to Dr. Jensen. Really appreciate it. This has been a wonderful kickoff to the series, and everybody have a great day. And thank you so much for coming. And thank you, Dr. Jensen. I appreciate your wonderful talk.
Thank you, Kathy.
Thank you.
Wonderful.
Bye-bye now.